So now let's talk about the assumptions that we're going to make when we do all this hypothesis testing. So assumptions. So the first one is going to be that our regression is linear in parameters. Two is that we have a random sample, or all of our y's and x's are IID. The third is that we have no perfect multicollinearity if we have a multiple regression. So maybe I'll put no perfect multicollinearity. So this is for multiple regression. I'm just going to put MR there. Or if it's just a simple regression, then we need some variation in our x variable, or x1, or whatever we want to call it. So that's the simple regression one. Remember, we had to change the assumption a bit when we started adding more variables in. The fourth is this big assumption that the expectation of u, or the error term, is mean independent of all the x's. If it was just simple regression, there'd just be one x. So that was that big assumption that was failing, and probably still is, even with multiple regression, because of unobservables. So remember that these assumptions here, these first four, were the ones, just as a review, gave us unbiasedness. So remember that meant the expectation of one of our slope parameters, or the intercept for that matter, is equal to the true value. The expectation of the beta hat is equal to the true value, the true effect of this variable. And then when we wanted to get a nice form of the variance, or we want to make a further assumption about the variance when we derive the variance, it's going to be an assumption that we're going to have to loosen later. Remember, we made an assumption the variance of u given all the x's was constant, and it was equal to sigma squared. So remember, this was homoscedasticity. And remember, these first four plus this fifth one gave us that the assumptions needed for the Gauss-Markov theorem, that we got the best linear unbiased estimators. And now we're going to make one more assumption, again about the error terms. We're going to make the assumption that they're normally distributed. So u this is distributed as a normal variable. We made this assumption. We can always make the mean equal 0, as we talked about. And above, we're just putting that as the variance. So we're making this assumption that the u's are normally distributed. This is going to help us determine the distribution of our test statistic here. Now, next module, after our next module, we're going to learn about, maybe we can loosen this assumption when we go over the asymptotics of ordinary least squares. But this is the new assumption right here, and what this is going to allow us to do is kind of talk about the distribution of our test statistic. So under assumptions, those assumptions we just listed, so 1 to 6. Under these assumptions, our slope parameter is going to have a normal distribution with a mean. So this is the estimated one because of the hat on it, right? Or the estimator. Has a normal distribution, so it's distributed, so that's that tilde, normally, with a mean. So the expectation, remember, of our beta hat j is equal to the true value, so that's why the mean of the distribution is the true value. And we have the variance of beta hat j, since that's the variance, right? So this is just saying our beta hat j has a normal distribution with a mean of the true value, and this is the variance. So remember, we can standardize variables, and so if we took our beta hat j and subtracted the true value, And if we somehow knew the standard deviation of our beta hat j, then this standardized version, then this standardization of beta hat j will have a normal distribution with a mean of 0 and a variance of 1. Now, one of the issues is we don't actually know the standard deviation, right? So a lot of times we're using the standard error. And so when we get to single regression, this is, based on this formula is how we're going to come up with our test statistic. So let's just write it out here. If we actually used the standard error, since we don't really know the standard deviation, so use the standard error as our estimate of the standard deviation, this is going to have a t-distribution with n minus k minus 1 degrees of freedom. So remember, this is the degrees of freedom. And so this t here is just representing a t-distribution. So it's a different distribution than a normal distribution. Though as this degrees of freedom correction gets larger and larger, it's going to start to look like a normal distribution. Okay, so under assumptions 1 to 6, our beta hat j is a normal distribution with a mean of beta j, the true effect. This is that variance. If we standardize it using the standard deviation of beta hat j, we'd get a normal, we'd have a normal distribution with a mean of 0 and a variance of 1. This is probably a lot of the stuff that you saw in your stats course before, where you kind of assume that you knew the distribution or you knew the variance of your random variable, so we can actually calculate the standard distribution. This is how you get that z stat, and you test it against the normal distribution. But here we probably don't know what the standard deviation or the variance of our random variable is, and so, or error term is. So we're going to estimate it. And so that kind of changes the distribution to be this t distribution.